Welcome to the deep dive. We've got a really fascinating stack of sources today, taking us way back in time. Not with a time machine exactly, but using frozen water. We're literally opening up cylinders of history.
Yeah, it's pretty amazing stuff. Ice cores, I mean, there were basically these long cylinders of ice that scientists drill out of huge ice sheets, Greenland, Antarctica, or sometimes mountain glaciers.
Right.
And because snow falls year after year, building up layer upon layer, the deeper you drill, the further back in time you go. These things can be, well, over 2 miles long in some cases.
2 miles.
Yeah, it's incredible. And the ice itself. Most famous cores go back maybe 800,000 years. But we have sources mentioning places like Allen Hills in Antarctica where they found ice that's like 2.7 million years old.
That is just staggering. 2.7 million years trapped in ice. So our mission today for this deep dive is to figure out how these, well, pretty fragile samples managed to capture so much information, Earth's ancient temperatures, the gases in the air back then, like CO2, even things like volcanic eruptions.
Exactly. And that's why one of your sources calls them the Rosetta Stones of climate history. It's a great analogy, actually.
Why is that?
Because it's not just one story they tell.
Yeah.
You get multiple independent lines of evidence.
Yeah.
Chemical clues, physical properties of the ice, the trapped air bubbles all locked together in the same sample. So the scientists can cross-check everything. It makes the data really robust.
Okay, that makes sense. So let's start at the beginning then. How does plain old snowfall actually become this incredibly detailed, dense historical record? It can't just be frozen water, right? There has to be more to it.
No, you're right. It's a process, a slow transformation, really.
Yeah.
As more snow piles up year after year, the weight presses down on the older layers underneath.
Okay, compressing it.
Exactly. Compressing it. This sort of compressed, grainy snow.
Mm-hmm.
It's not solid ice yet. It's still got air pockets connecting through it. That's called firn.
Firn. Okay, I think I've heard that term. So it's like halfway between snow and ice.
Yeah, it's a good way to think about it. Still porous. But then comes the really crucial point. As it gets buried deeper and the pressure builds, it eventually reaches a critical density. The sources say around 830 kilograms per cubic meter.
Right.
And at that density, the little pathways connecting the air pockets get squeezed completely shut. The firn becomes solid, impermeable ice. And this is the key part. The air that was in those pockets gets trapped, sealed off into tiny individual bubbles.
Ah, I see. So those bubbles are like tiny fossilized samples of the atmosphere from that exact time.
Precisely. Perfectly preserved samples. But here's something that might surprise you, and it's really important for understanding the data. There's always an age offset. The ice itself is older than the air trapped inside those bubbles, sometimes much older.
Wait, hold on. Why? I would have thought the air gets trapped right when the snow falls. How can the air be younger?
Well, it's because that whole process of turning firn into ice, the sealing off process, it takes time. And how much time depends heavily on how much snow falls each year, the accumulation rate. So think about a place like Greenland, where you get a lot of snow, relatively speaking. There, the layers build up faster, the pressure increases quicker, and the firn seals into ice relatively quickly. So the air trapped inside might only be, say, 230 years younger than the ice surrounding it.
Okay, a couple centuries difference. That seems manageable.
Right. But now contrast that with somewhere like Dome Sea, high up on the Antarctic plateau. It's incredibly dry there, very little snowfall.
Super low accumulation.
Exactly. So it takes a really long time, thousands of years, for enough snow to build up to create the pressure needed to seal those air bubbles. Our sources mention that at Dome Sea, the ice could actually be around 2,500 years old by the time the air inside it finally gets locked in.
2,500 years difference. Wow. Okay, that definitely complicates things. You can't just, subtract a fixed number.
Yeah. Absolutely not. It means scientists have to build these really complex models. They have to figure out exactly how the firn compacted, how the density changed, when those bubbles lightly closed off over thousands of years. All to correctly align the age of the air sample with the age of the ice sample it's trapped in. It varies hugely depending on the location and past climate.
That's a lot more involved than I realized.
Yeah.
So, okay, we've got the ice itself telling us about temperature, and we've got these bubbles of ancient air. What else gets trapped in there?
Oh, it's like a complete snapshot of the environment at the time. It's amazing what they find. You get soot and ash particles from ancient forest fires or huge volcanic eruptions halfway across the world.
Oh, yeah.
You can find tiny grains of pollen, which tell you about the vegetation nearby, and even, believe it or not, minuscule micrometeorites, tiny bits of space dust that drifted down.
Micrometeorites.
That's incredible.
Just patiently collecting cosmic dust over millennia.
Yeah. And even the physical structure of the ice in polar regions can tell you something.
Yeah.
You often see these visible bands alternating lighter and darker layers.
Uh-huh.
That's usually the difference between summer snow and winter snow. Summer layers tend to be a bit coarser, maybe lighter, because of sunlight effects like sublimation and frost forming. Winter layers are denser. These visible bands are often the first thing scientists look at. They can help count the initial layers, at least near the surface.
Fascinating. Okay, so that's how the record forms naturally. But actually getting these things out of the ice, especially from miles deep in places like Antarctica, that sounds like a huge engineering challenge.
Oh, it absolutely is. Forget just digging a hole. For shallower cores, maybe down to 50 meters or so, they can use augers, sometimes hand-powered, sometimes engine-powered. Simple enough.
Okay.
But for the really deep stuff, the ancient ice, you need specialized drills, usually electromechanical ones or sometimes thermal drills that use heat to melt through.
Yeah. And I imagine drilling 2 miles down into solid ice presents. Unique problems, like just the sheer weight of all that ice pressing down.
That's exactly it. It's called the deep hole problem. Below about 400 meters or so, the pressure from the overlying ice is so immense that it actually makes the ice flow, trying to squeeze the borehole shut.
So that the hole collapses behind the drill.
It wants to, yeah. To stop that, they have to fill the hole with a special drilling fluid. This fluid exerts counterpressure, keeping the borehole stable and open.
Right, like balancing the pressure. What kind of fluid do they use? Does it have to be special?
Very special. The key property is low kinematic viscosity. Basically, it needs to flow really easily without much internal friction or gumminess.
Why is that so critical?
It all comes down to trip time. That's the time it takes to pull the whole drill assembly up out of the hole to get the core segment you just cut, and then lower it all the way back down again to drill the next section.
Ah, okay. Miles up, miles down.
Exactly. If the fluid is too thick or viscous, it creates a lot of drag, slowing down that whole trip. It sounds minor, but on these huge multi-year projects, a slow trip time due to the wrong fluid could add months, maybe even a whole year, to the project schedule and budget. It's a massive logistical factor.
Wow. So the project's success could literally hinge on how easily some fluid flows deep underground.
Pretty much.
Yeah.
That's also why the technology evolved. Older rotary drills required pulling out the entire drill string each time. Modern deep drilling usually uses cable-suspended drills. The whole motor and drill barrel hangs on an armored cable, so you just winch that part up and down. Much faster, much more efficient for deep ice.
Makes sense. But even once you've drilled the core, getting it back to the surface intact must be tricky. Does the ice itself cause problems during retrieval?
Oh, definitely. One of the biggest headaches is something called the brittle ice zone.
Brittle ice.
Yeah. There's a specific depth range, like at the Ways Divide project, it was roughly between 500 and 1,300 meters down where the ice is particularly fragile.
Why there specifically?
It's because those air bubbles we talked about.
Yeah.
In that zone, they're trapped under incredibly high pressure from the overlying ice. We're talking hundreds of times atmospheric pressure.
Okay.
So when you drill out a core section from that depth and bring it up to the surface relatively quickly, that pressure is suddenly released.
Ah, and the bubbles expand rapidly.
Exactly. Bang. The expanding air can cause the ice core to crack, violently shatter, or spall, basically, pieces fly off. You can lose huge chunks of valuable core.
So how do they deal with that? You can't just bring it up slowly over months.
No, but they have techniques. Sometimes they have to retrieve the core from that brittle zone very carefully and then let it relax in storage at the drill site, often at a controlled temperature just below freezing, for months, sometimes up to a year.
A whole year just sitting there?
Yep. Allowing the internal stresses to slowly equalize before they even try to cut it or ship it for analysis, it requires incredible patience and planning.
The scale of these operations is just mind-boggling. These big international projects, like E-Strip you mentioned, must involve enormous infrastructure, building camps out there, flying everything in.
Absolutely. Years of planning, massive logistical support, often involving military airlifts like the U.S. Air National Guard, providing ski-equipped planes just to get equipment and people in and out of these incredibly remote locations. All that effort just to get the ice samples.
And then the real science begins back in the lab. You mentioned cross-referencing different records within the core. How do they actually start figuring out the age, especially deep down where those visual layers disappear?
Right. Counting the annual layers visually works well near the top, but deeper down, the ice flow stretches and thins those layers until they become indistinguishable. At a place like Vostok, with low snowfall, you might only be able to reliably count layers for the top, say, 55,000 years or so.
So for the older ice, like that 800,000-year record, they needed other methods.
Exactly. They rely heavily on reference layers. Think about massive volcanic eruptions. Tambora in 1815 is a classic example. An eruption like that throws huge amounts of sulfur dioxide high into the stratosphere, which then spreads globally and eventually falls out as sulfuric acid. This acid leaves a distinct spike in the electrical conductivity of the ice layer formed that year.
Ah, like a fingerprint in the ice.
Precisely. And because it's a global event, you find that same acid spike in cores from Greenland, Antarctica, mountain glaciers, everywhere. It acts like a time marker, allowing scientists to perfectly synchronize the dating between different cores across the planet.
That really reinforces that Rosetta Stone idea, finding the same marker everywhere.
It does. And for synchronizing even further back, connecting Greenland and Antarctic records over hundreds of thousands of years, they can look at gases. Things like methane concentrations or the ratio of nitrogen to oxygen isotopes in the trapped air. These tend to fluctuate in sync with long-term orbital cycles, the Earth's wobble and tilt, which affect climate globally. So they provide another set of anchors to link the timelines.
Okay, let's talk about temperature. That's probably what most people think of with ice cores. How does the actual water molecule, the H2O, record the temperature from when the snow fell?
It comes down to isotopes again, but this time isotopes of oxygen within the water molecule itself. Specifically, the ratio between the common, lighter oxygen-16 isotope and the rarer, heavier oxygen 18O.
Right. How does that relate to temperature?
Well, think about water evaporating from the ocean. Water molecules containing the heavier 18O are slightly less likely to evaporate than those with the lighter 16O. And as water vapor travels from warmer regions towards the cold poles, the heavier 18O tends to rain out more easily along the way.
Okay, so the further the vapor travels and the colder it gets.
The more depleted the remaining vapor becomes in that heavier 18O isotope. So the snow that eventually falls over Greenland or Antarctica during colder periods will have a lower ratio of 18O to 16O compared to snow that falls during warmer periods.
I see. Colder means less heavy oxygen arrives.
Exactly. Scientists measure this ratio, and they express it as a delta value ADO, usually a negative number. Lower, more negative delta values mean colder temperatures when that snow originally formed. It's an incredibly sensitive thermometer reaching back hundreds of thousands of years.
And this isotopic data has led to major discoveries, right?
Absolutely. It was this kind of data combined with direct temperature measurements down the borehole itself that really revealed the existence of incredibly rapid climate shifts in the past, like the Dansgaard-Oeschger events.
Tell us about those. What were they?
These were really dramatic warming events, primarily seen in the Greenland ice cores, that occurred repeatedly during the last glacial period, the last ice age. The isotopic records showed temperatures jumping up significantly, sometimes several degrees Celsius, in potentially just a few decades.
Just decades, not centuries or millennia.
Potentially decades. Really abrupt warming spikes, followed by a slower cooling back into glacial conditions. It completely changed our understanding of how fast climate systems can shift. It proved climate change isn't always slow and gradual. That's, a crucial lesson from the past. Now, going back to those air bubbles, the paleoatmospheric sampling, what were the big early findings from analyzing that trapped air?
One of the most fundamental findings established pretty early on was the direct link between CO2 and temperature over glacial cycles. The data clearly showed that during the peak of the last ice age, the last glacial maximum atmospheric CO2 concentration was about 30% lower than it was in the pre-industrial era.
So a direct correlation over long timescales.
A very strong, clear correlation. It provided that crucial long-term baseline showing how tightly CO2 and global temperature are linked long before human influence became dominant.
And can we see that human influence now in the cores? Can we track purely man-made compounds?
Oh, absolutely. A perfect example is CFC's chlorofluorocarbons. These are entirely artificial compounds created for refrigerants and aerosols.
Right, the ozone-depleting ones.
Those are the ones. Since they only started being produced industrially around the mid-20th century, guess when they first appear in the ice core record?
Around 1950. Exactly.
Yeah.
You can pinpoint their appearance in the snow layers, dating to about 1950 onwards. It's a really sharp marker of the start of the great acceleration of human impact on the planet's atmosphere.
It's amazing that the ice captures everything from natural cycles to the dawn of the synthetic chemical age. But you also mentioned glaciochemistry revealing even deeper history.
Yes, that's another fascinating angle. Glaciochemistry looks at the trace chemicals dissolved in the ice itself, Measuring things like electrical conductivity can show seasonal cycles like spikes in sea salt aerosols during stormy winters or hydrogen peroxide linked to summer sunlight. But it also picks up pollutants.
Pollutants from Melone.
Well, this is where it gets really surprising. Analysis of lead levels, particularly in Greenland ice cores, showed some unexpected patterns. There were distinct peaks in lead concentration way back in antiquity.
Lead pollution from ancient times.
Now, it turns out these peaks correlate incredibly well with specific periods of the Roman Empire. When Rome was expanding, mining silver lead is a byproduct of silver smelting and engaging in large-scale warfare which used lead. The atmospheric lead pollution increased. That lead got carried by winds all the way to Greenland and was deposited in the snow.
Wow.
Then, during periods of Roman decline, plagues, or civil wars, when mining and smelting activity dropped, the lead levels in the Greenland ice cores also dropped significantly.
That is absolutely incredible. The ice in Greenland was basically keeping a silent, unbiased economic and, well, military history of the Roman Empire thousands of miles away.
It's an amazing link, isn't it? It connects atmospheric science, glaciology, and ancient history in a way no one really predicted, a completely unexpected window into past human activities.
So wrapping this up, we've journeyed from falling snow to these incredibly complex ice cores, these multi-layered history books holding records of Earth's climate, the atmosphere, volcanic events, and even, remarkably, ancient Roman industry and warfare.
Yeah, it's a phenomenal archive. And the knowledge we get from them, especially those really long cores like the 800,000-year Epicodome sea record from Antarctica, is absolutely fundamental for testing and improving the climate models we use to understand the present and future. They give us the long-term context, the baseline that goes far beyond human records.
But as we've touched upon, there's a real sense of urgency now, isn't there? The archive itself is potentially under threat.
It is, unfortunately. As the climate warms, especially in some lower latitude or lower altitude glaciers, and even potentially affecting the surface layers of the big ice sheets, there's a risk of meltwater percolating down.
And that would mess up the layers.
It could completely ruin the record. Meltwater can wash away or redistribute those trapped aerosols, gases, and chemical signals, essentially blurring or erasing that perfectly preserved chronological information. The history gets scrambled.
So the time capsule starts to leak.
Exactly. That's why you have initiatives now like the Ice Memory Foundation. They're actively working to drill and retrieve duplicate cores from glaciers, seen as particularly vulnerable around the world. The plan is to then transport and store these heritage cores in a dedicated, ultra-cold storage facility being built in Antarctica.
Like a global seed vault, but for ice history.
Precisely. Creating a permanent archive, safeguarding this irreplaceable data for future generations before the original glaciers melt away or their records become corrupted by warming. It really is a race against time to save time itself, in a way.
A critical mission. We've talked about how the current deep cores, going back 800,000 years, strongly show those 100,000-year climate cycles, the ice age rhythms that dominated the recent geological past.
That's right. The Milankovitch cycles are very clear in that time frame. But here's something for you, the listener, to think about. The next frontier in ice core science is pushing even further back. There are major international efforts planned or underway to try and retrieve ice that's older than 1 million years, maybe 1.2, 1.5 million years old or more.
Why that specific time frame? What are they hoping to find?
Well, climate scientists know that before about 1 million years ago, Earth's climate system seemed to operate on a different frequency. The dominant ice age cycles were closer to 40,000 years, not 100,000 years. Finding continuous ice core records from that older period across that transition could reveal why that fundamental shift in Earth's climate rhythm occurred.
So capturing evidence of a completely different climate state.
Exactly. So the provocative thought is this. If we can find ice old enough to show us the mechanics behind that massive shift from 40,000-year cycles to 100,000-year cycles, what other fundamental long-term patterns or climate behaviors might still be locked away in the oldest, deepest ice we haven't even reached yet? What other major transitions in Earth's operating system are waiting to be discovered down there?